morning everyone, myself Tsering Dema of BSc first year of Namche Government College. Today in this video, I am going to talk about Gauss law. First of all, introduction to Gauss law. Gauss law was named after German scientist Carl Friedrich Gauss in 1835 but was not published until 1867. Gauss law is also known as Gauss flux theorem and Maxwell's first equation. Gauss law is relating the distribution of electric charge to the resulting electric field. Gauss law allows us to find electric field without needing to integrate. Using Gauss law, the electric field of a given charge distribution can be calculated. Now, the principle of Gauss law says that the Gaussian law is a method wisely used to calculate the electric field from symmetric charged object. The Gauss law states that electric net flux through any Gaussian surface is directly proportional to the net charge enclosed by the surface. That is, flux is equal to net charge by epsilon naught, where epsilon naught is the permittivity of vacuum. Derivation of Gauss law. Deriving Gauss law using Coulomb's law. There are two cases. Case 1, spherical surface enclosed single point charge. Let us suppose we have a sphere with radius r and a positive charge q, and suppose we have a single point charge with a magnitude of e. There is a small surface called Gaussian surface dA. Now we know that Gauss law is equal to electric flux is equal to integration of Gaussian surface E vector dot dA vector is equal to charge enclosed by the surface by epsilon naught. Equation number 1. Now simplifying equation 1, we get net electric flux is equal to integration of E vector dot dA. Now E vector is a constant. E vector is equal to integration of dA vector. Now E will be replaced by Q by 4 pi epsilon naught r square. E will be replaced by Q by 4 pi epsilon naught integration of dA, since E is equal to Q by 4 pi epsilon naught r square. Now Q by 4 pi epsilon naught r square integration of dA is equal to A. Now Q by A is equal to 4 pi epsilon naught r square. A will be replaced by 4 pi r square divided by 4 pi epsilon naught r square, since A is equal to 4 pi r square. Now 4 pi will be cancelled, r square will be cancelled, Q by epsilon naught. Now therefore electric flux is equal to Q by epsilon naught. That is Gauss law. Case 2. Irregular surface enclosing the same point charge. Let the same type of field lines passes through the surface A1 and A2. Electric flux is equal to integration of A1 E dot dA is equal to integration of A2 E dot dA is equal to Q by epsilon naught. Therefore, this implies integration of E dot dA is equal to Q by epsilon naught. Gauss law in dielectric. Consider a parallel plate capacitor with equal area A and charge density sigma, and there will be a vacuum between the two plates, as you can see in the diagram. This following diagram explains the law in dielectric between two parallel plates. Then we can evaluate field vector epsilon naught in the region between the plate using the Gauss law. Let us consider a Gaussian surface with cuboid shape and one face is Gaussian. The flux will not pass through it, and then the flux will not pass through the perpendicular face to this face. Therefore, the flux will only pass through the face which is parallel to the positive plate. Consider epsilon naught constant of Gaussian surface, and theta is the angle between the field vector and area vector. Double integration of S epsilon naught dot d alpha is equal to Q by epsilon naught. Again, double integration of S epsilon naught d alpha cos theta is equal to Q by epsilon naught. Double integration of S epsilon naught d alpha is equal to Q by epsilon naught. Epsilon naught is constant, therefore the epsilon naught will be outside of the integration. Now epsilon naught is equal to double integration of S d alpha is equal to q by epsilon naught. Epsilon naught A is equal to q by epsilon naught. Q by epsilon naught is equal to q by epsilon naught by A. Here q is equal to A by sigma. Epsilon naught is equal to A by sigma by epsilon naught A. A will be cancelled out, so epsilon naught is equal to q by epsilon naught. Gauss's law for magnetostatic. This law for magnetism applies to the magnetic flux through a closed surface. In this case, the area vector points out from the surface. Since magnetic field lines are continuous loop, all closed surfaces have many magnetic field line going in and out. Hence, the net magnetic flux through the closed surface is zero. Net flux is equal to integration of B dot dA is equal to 0. Therefore, the net sum of all current in the enclosed surface is null. Gauss law for charges was very useful method for calculating electric field in highly symmetric situation. That is why Gauss law for magnetostatic is used very rarely. Now, let us talk about the advantages and disadvantages of the Gauss's law. First, let me tell about you the advantages of the Gauss's law. The advantages of the Gauss's law are as follows. When we compare to the Coulomb's law, it provides specific force direction with proper accuracy with its proper general cases. Gauss's theorem is more efficient in all objects and surface for purpose of finding an electric field, and also it will work effectively in the distribution process when compared with Coulomb's law. Now let us see the disadvantages of the Gauss's law. The disadvantages of the Gauss's law are as follows. The limitation of the Gauss's law is that it will only calculate the electric field in some special cases. We cannot use Gauss's law in the calculation of the field due to electric dipole. Applications of Gauss's law. There are many applications of Gauss's law, but the two major applications are: number one, electric field due to infinitely charged wire, and second is electric field due to infinitely placed sheet. First, let us talk about the electric field due to infinitely charged wire. Consider an infinitely long wire with a linear load density of lambda and a length of L, as you can see in the diagram. To calculate the electric field, we assume that the Gaussian cylindrical surface is due to the wire symmetry. As the electrical field E is radially in the direction, the flow through the end of the cylindrical surface will be zero. As the electric field and the area vector are perpendicular to each other, the only following electric flux will be through the curved Gaussian surface. As the electric field is perpendicular to every point of the curved surface, its magnitude will be constant. The surface area of the curved cylinder surface will be 2 pi RL. The electric flux through the curve will be E into 2 pi RL. Now, according to Gauss law, electric flux is equal to Q by epsilon naught. Electric flux will be replaced by E into 2 pi RL is equal to lambda by epsilon naught, where Q is equal to lambda. E is equal to lambda 2 pi epsilon naught. Vertically, the above relation is E vector is equal to lambda by 2 pi epsilon naught R n vector, where n vector is a radial unit vector pointing the direction of the electric field E vector. Now the second part is electric field due to infinite plate sheet. Imagine an infinite plate. The position of infinite plate sheet is given in the figure below. Infinite charge sheet. The direction of the electric field due to the infinite charge sheet will be perpendicular to the plane of the sheet. Let's consider a cylindrical Gaussian surface whose axis is normal to the plane of the sheet. The electric field E vector can be evaluated from the Gauss law as: according to the Gauss law, electric flux is equal to Q by epsilon naught. Electric flux is equal to EA negative EA. This implies electric flux is equal to 2EA. Then we can write 2EA is equal to sigma A by epsilon naught. The A cancels out with which means electric field due to infinite plate sheet is independent of cross-sectional area A and equal to E is equal to sigma by 2 pi epsilon naught. In vector form, the above equation can be written as E vector is equal to lambda by 2 pi epsilon naught r n vector, where n vector is a unit vector depicting the direction of electric field perpendicular and away from the infinite sheet. Thank you.